So what I've prepared here is a question and its solution. So I want to start with a question and the solution, just to start off this video. Okay, so the question is basically asking, you have this element, tin, and you have its electron configuration, or you have to deduce its electron configuration. And once you've done that, it's asking you how many p orbitals have at least one electron. So what I've done is I've written out, according to this schematic and the periodic table, the electron configuration of tin. So we have a 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, and 5p2. So I've circled all the p sublevels because that's the sublevels that we're interested in. And we have 3 filled p sublevels here, right? So each p sublevel contains 3 orbitals. So we have 3 times 3, and we have 9 orbitals with at least 1 electron. They actually have 2 electrons each, which is the maximum. So this is 9 filled orbitals. And then we look at the 5p sublevel, and we notice that there are 2 out of 3 orbitals that have electrons in them, and they have 1 electron, which satisfies this greater or equal to 1 electron condition. So in total we have 2 plus 9, which gives us 11 orbitals, which are found in the p subshell with at least 1 electron, so that it can be 1 or 2. So that is the solution to the first question that I'm going to be looking at today. So the next question is this. How many electrons are there in all the d orbitals in an atom of barium? So we want to calculate the total number of electrons this time. So let's head back here. Total number of electrons in d orbitals of barium. So let's find barium on the periodic table. So looking for barium, where is barium? So barium is going to be over here. So it's atomic number 56. Z equals 56. So we know there's going to be 28 pairs of electrons. And let's draw the diagram since it's quite helpful. 4s, 5s, 6s. Then we have the 2p, 3p, 4p, 5p, 6p. And then we have 3d, 4d, 5d, 6d. And then we have the 4f, 5f. So it's going to be like this. As follows, like this, and that's all we'll need. So let's start drawing this out. The 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. So this is not going to be totally realistic, so we're going to drop down here for a bit. So we have the 5s, and then we have the 4d, and then we're going to have the 5p and 6s, but we won't be needing that. So we know that up to 3d we're going to actually have 30 electrons. So something to keep in mind is that when we go up to 4s, that's 20, and we know every d sublevel is going to have 10, so we're going to have 30 after this sublevel is filled. So that's going to be 30, right? So we need 26 more. So filling the 4p, that gives us 36, 37, 38. So after this is going to be 48. So So that's 48, 49, 50, 51, 52, 53, 54, 55, 56. Okay, so we end up needing the 6s sublevel. So now we want to find the total number of electrons in d orbitals. So as I did before, let's try to select all of the d orbitals. So we have, let's start from the bottom, we have the 3d and 4d. And since these are all filled, we're going to take the number of positions here. So the number of orbitals multiplied by 2. So we're going to have 5 orbitals here, 5 orbitals here. So we have 10 orbitals. And how many electrons per orbital? Times 2 electrons per orbital. It's going to give us 20 electrons in total. And we can go ahead and check that answer. And yes, it's 20. So that's the answer to that question. So now let's take a look at the next question. Let's go back here. State the electron configuration of the ion. In this case, it's going to be a positive cation. Okay. So let's find cadmium on the periodic table, since we have a 2+ cadmium ion. So we're going to find the electron configuration of cadmium 2+ ion. So like always, we want to start out by finding the cadmium ion. So in this case, it's 48 on the periodic table. So let's write down the atomic number. So Z is the symbol of the atomic number. So it's going to be 48 in this case. So we know there's going to be 24 pairs of electrons. And we can go ahead and draw the diagram again. Okay, so now let's try to draw it out. We have a 1s, 2s, 2p, 3s, 3p, 4s, 3d. So this is going to be 30. And then let's keep going. We have a 4p, we have a 5s, and then we have a 4d, and then we have a 4p. Okay, so let's fill this out. So when filling out the lower sublevels, it's not really important to follow Hund's rule, because you know that you're far away from the actual atomic number or actual place in which you stop the electron configuration. But if you're new to this, I think it's important that you always follow all the principles. So obviously you're going to follow Pauli's exclusion principle, so the different spins and the maximum of 2 electrons per orbital. You're definitely going to follow that. And Aufbau's principle is just building up, so you're going to follow that as well. Hund's rule, typically I only follow it when I know I'm getting close to the actual atomic number or actual number of electrons. So we're up until 30 right here. Like, let's just say it's 30 electrons, and then we can start becoming a little more careful. So we're going to have 6 here, so 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Okay, so we won't be needing this 4p sublevel. So this is the electron configuration of cadmium. So this is what we have, cadmium, right? We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s. 3d10, 4s2, 4p6, 4d10, 5s2. Except we want to find the electron configuration of cadmium 2+. So when we have a cadmium with 2+, we know that it's going to lose electrons. If it's 2-, it would be gaining electrons, but we have a 2+, so it's going to be losing 2 electrons. And we want to take it from the highest energy sublevel. In this case, it's going to be the 5s2. And since it only has 2 electrons, we're getting rid of both of them. So what we end up with is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10. And let's practice writing it as a noble gas configuration. So let's head back here. And where's cadmium? Cadmium's right here, right? So the noble gas we're going to be using is just going to be Krypton. Let's go back. So Krypton is actually going to be, it's going to replace everything before the 4p6 subshell. So we're going to have Krypton, and then we're going to have, typically we're going to have like 5s2, usually start with the S sublevel after a noble gas abbreviation. But in this case, we're going to be removing it since we have an ion, right? So we have cadmium 2+ ion. It's going to be Krypton and then a 4d10. If we want to abbreviate the cadmium atom, which is neutral, we're going to have Krypton. So this is more standard practice. We're going to have 5s2, and then we're going to have a 4d10. And that's going to be it for this video. In the next few videos, I'll just be doing more questions from the textbook and trying to explain the best way to solve it. So hopefully this video helped, and see you next time.